but with those added spanses of force, the weight, it doesn't really go over it. You know, it does a little bit on when it's got a partial, but not the whole with another one stacked on it, and so
At box office, it finally sold
it was a little bit trying. I'll tell you.
6.5 in the first week. But
Yeah.
it
Yeah,
has sold over an estimated 1.1
All right,
yeah, that doesn't even matter though.
million
Let's,
units.
It's about the inches.
let's get going.
And signs.
Box office growth.
I've marked off the board so that we won't, I won't draw outside of the margins today for you. But before we look at anything specifically, I got a couple just kind of general emails about, can we look at some things today? But then Rush and I were looking at some things specifically. Hopefully before we short circuit
I was
that
gonna say
entire
before
road.
we all get electrocuted here. Actually, I think we have a little mop.
Yeah, the mop's probably in the other room, but.
Well, we got that.
Clean up on aisle one.
Marshall, are you okay?
Yep.
All right. So let's look at a couple of just general examples of the force polygon and how we get about resolving these problems. Okay, so how they're laid out in your text is that you've got a couple pin connections and a cable joining to some weight. Okay? You know, we talked about last time how this could model any number of types of things, right? We could be talking about pulling down on top elements of a truss over a bridge deck. We could be dealing with using a crane to pick elements. We could be using, this could be supported from some sort of roof or ceiling element, okay? So the few things that we need to know is we need to know our distances and we need to know what our angles are. And then that will help us construct our force polygon, okay? So we'll say that it's 4 foot here, and we'll say that we have 12 foot here. Let's actually change that. Let's make this 10 foot. We'll make this 3 foot. And we'll make this 8 foot. This will make our solution a little bit easier. Okay? So if we mark this down, what is this distance going to be? 4 feet, right? Okay. So we talked about the 3, 4, 5 triangle last week. What do we remember about the angles in a 3, 4, 5 triangle? What are we going to have? We're going to have a 30, 60, 90 triangle, right? So down in this angle, we'll have our 30 degrees, and up here we'll have our 60 degrees. Sorry.
Sorry about that? Okay.
We're gonna have 60 degrees down here, we're gonna have 30 degrees down here. Now, the specific instances that I saw of people constructing the force polygon, what they were doing is they were taking the 300-pound load and dropping this down and then extending this force just along its line of action, down in this direction, okay? And then joining and making their triangle. What is going to tie us up with this equilibrium condition with respect to what our situation is in the field? Does this force polygon represent how we're set up?
No.
It doesn't, right? What's that?
Not using another half.
We're not taking into account what's going on with this component of our system, okay? This polygon would work if our setup looked nope, it wouldn't work for that either. it would work if this was what our support system looked like, okay? But because we have this set up, our polygon has to represent what these forces look like, okay? So we can construct our polygon in any way that we choose, so long as we are not changing the line of action of any of our forces under consideration, okay? So if we have this guy with the same angle, which I did a marginally good job of representing that, and if this represents this line of action, okay, now we have our equilibrium conditions. Okay? Does that make sense to everybody? Why this is the case? Getting some nods, but not nods from everybody.
That was, yeah, I remember when, with our correspondence, you know, and I did my best to rotate that to
Yep.
represent, because I knew where, you know, we pointed out where we went wrong there
Yep.
with the line of action, but I worked with Kurt and the way he brought it down right from the top, and it just seemed to make more sense. Dropping from
Brought right, what down right from the top?
So you take the right half and then draw a line from down from the 60 and over,
Yep,
So straight down there,
straight down and then
over to the
over.
30,
And then the force coming from that line down is 150.
100.
Or-
Oh, on this, yeah, in this
Yeah.
example, 150,
And then you can use the law of sines to solve that way.
because you know the angles.
and, okay, so you're assuming it's the same as this reaction?
Yes, that reaction is 150. Yep.
Good. Yeah, that would be another way that you could look at it.
And
But
that's
that only works
because
at
it's
different
equal.
angles.
You know what I mean? The both force lines of actions are
Yep.
equal. It's not one of those.
Correct.
This one's longer than that one, so you have
Correct.
to change. You know what I mean?
Yeah, so that one will work when you have symmetry, right?
Mm-hmm.
When you're able to mirror over the plane. For the second problem, you may not be able to do that. You would have to solve for your reactions to determine what the reactions are. So I caution you on trying to use that for
Right.
every one of those problems. Okay?
Yeah.
But now at this point, what do we know about this polygon? We don't need to worry ourselves with these items.
So
Do we know the magnitude of this force?
Yes, 300 pounds.
It's 300 pounds, okay? Do we know what this angle is?
To the right.
It's a right angle, right? Because in here, although it doesn't look like it because I made a poor representation, but we have a right angle, okay? So we have to have a right angle here. Looking at our drawing here, and as it translates to here, can we say anything about either this angle or this angle?
What's a 3, 4, 5, right?
It'll still be a 3, 4, 5, yep.
So it'd be 60 and 30.
Top will be 60.
Top will be 60. Bottom will be 30 degrees, okay? So we know that because it's a 30-40 triangle, but keep in mind also, our load is being applied in the vertical condition, okay? We're applying load in a vertical condition here. If we don't change our line of action in translating the force in this member from here to here, doesn't this angle have to equal this angle? If we haven't changed any of our lines of actions?
Correct.
Correct.
Yeah?
Mhm.
Everyone on board with this? Or not so much? Should we look at another example? I'm fine with looking at another example.
Can we do one where because in the book, I don't get it because they don't give us the angles.
Are you talking about the one that's lopsided?
B?
Yeah.
Okay, we can look at that, Justin, yeah?
Why is that a 30-60-90 triangle? Because aren't the two legs-
This one here?
Yeah, so the two legs are gonna be the same length, aren't they? Yeah.
So you got a 3 and a 4 foot,
See, you're.
and it's a right triangle.
Skipped a step, I think.
Well, because I thought you were taking the other. So it's gonna be three.
You took the other
so
angle already.
I thought you were taking both.
Yep.
From the original, so you're taking that one and then the other side.
Yep.
Making a triangle out of it, right?
Yep.
those are the same length.
Yeah.
So why wouldn't it be
just
a,
the right half?
why wouldn't it be a
Oh,
45,
it's-
45, 90?
Yeah.
Yeah, so it'd be equilateral.
Yeah, you've got a good point, you've got a good point. Yes, we should have drawn it,
I was looking at it as just that half, so just rotate it.
we should have drawn it, let's see, so we want. Dick. It's a little bit better right angle. Tough center. That's still not right. Okay? Is that better? So now we would have 4 feet here, 8 feet here. And that's a good scale right there.
Oh, see, I thought,
So you're changing it again.
in your first example, it looked like the 8 foot was the whole length. and
Yeah.
Yep.
It was only 4 foot.
Yep,
So why, are you moving the line over? You can't do
Now
that.
you're doing a new problem?
That's what that's
not
supposed to
that
look like.
problem.
no, I'm just changing the geometry. No, Justin's point is, I drew an equilateral triangle. Over here.
All I was asking is that triangle you drew down there.
Yep,
Should be a 45, 45, 90, right?
Yeah.
yes, with how I drew this.
That's
Yes.
all I was looking for.
Yep.
So that's just drawn incorrectly.
Yeah.
That's a 12-foot span.
Yep,
Mm.
Okay, so it looked like that was 8 foot, and then it was chopped in
Correct.
half, and here's 4 foot.
correct.
Okay,
Yep.
I get it.
My scale is just incorrect.
All right, okay.
Yep, yep. The joys of freehand drawing on a board.
Okay.
Okay. So should we look at, let's see on page 17, do we want to look at C? Would it help to look at C?
Can we like go through a whole problem and get
Yeah, can we
answers?
just knock that one
Oh,
out?
yeah.
Say like it's 4 foot on each side, the whole length, 10 foot. So just change that little triangle to 45, 45, 90.
And
That way it's
can you,
similar to the
like,
first
set
one.
up
that we
the
had.
formula that I'm supposed to punch in my calculator? Like, I'm totally lost here, man.
We still haven't found the answer to like, any of these.
No, no, we have not.
Kurt, so am I correct in saying that on B, on 17, we're wrong then?
Why can't you just do the?
What?
Oh, for A.
Shall you want to see the answer number 8? Letter A.
So once you do
So then how would you set, so then how would you set
Sine
this
90.
up?
or
No idea. Math?
sine of 90 over 300.
Well, we know all 3 of our angles,
Yeah.
and we only know magnitude on one side. So of the 2 equations that we have, law of cosines or law of sines, which one allows us to solve for that case?
Awesome.
Why do you need to use a law? Why can't you just use regular sine?
You could use sine as well.
Because it's just easier and it's the right triangle.
You could use that as well, absolutely. Is that what you would like to do?
Well, no, I think using normal sine is just easier than writing out a whole law of cosine or law of sines.
Well, remember that law of sines is just sine of A is to A as sine of B is to B,
Yeah.
right?
But isn't it easier just doing sine of 45 equals x over 300?
It can be,
I
yeah.
That works because it's 90 though.
think it's
Yeah,
easier
it's
to
not,
do
it's
it.
not always gonna be in.
It's not always gonna be a 90 degree though, man.
Yeah.
90, the sine of 90 is 1, so that works.
Well, also, it doesn't matter if you have a right angle or not. Both of these will work in all cases. It's just going to depend on what the individual is preferring. So, John prefers taking the sine of an angle as a ratio.
Yeah, I do prefer.
to what the magnitudes are. Okay.
Great, that's,
What's the question?
So now once we do that, our side lengths become magnitudes, not just lengths. No.
No, that's what they always been.
They always are.
No. We have to be careful.
Yeah.
Our side lengths, the length of our material, is not going to be directly proportional to the magnitude of the force within the member. And that's what we're going to look at in the next chapter, okay? Because keep in mind, what we're looking at here, we're looking at a three-dimensional element in 2 dimensions, right? What is the width of this cable? I have no idea, right? But, and I don't want to get the cart too far ahead of the horse here, but if I have a steel cable here and I need to cover 10 foot and I have 200 pounds, how would I control that? If I only have 10 feet to work with, I would control it by using a thicker or a thinner cable, right? If I'm not tied to this length, I can adjust how much load I can take by shortening it and using a wider cable, or I can make a longer span with a thinner cable. Okay? So, again, I don't want to jump too far ahead of us, but I don't want you to get into the mindset that the magnitude of the force in the member is going to equal the length of the member. That is not necessarily going to be the case in the real world.
so right now we're just finding the length.
Oh, we're finding the
Nope, we're finding the magnitude of the force.
I'm talking on that to your force polygon.
Yep,
Find
In the-
side length
in the
now,
force
it is
polygon.
now gonna be magnitude.
yep. In the force polygon, the length of that leg will be the magnitude of the force.
Right.
Yep. That is a correct assumption to make, okay? It is not, however, going to tell you anything about this distance of the cable to the, from the reaction to where the load is applied. Okay? Do we want to look at 17C, or problem C on page 17?
Yes, please.
Okay.
So is that completely solved?
No, you just have to put something here.
Well, now it just becomes X equals 300 pounds times sine of 45.
Which is 212.
And it's what, 0.71 something, right?
Yeah.
Okay. So it's about 215 pounds,
212.
212? Yes, Justin?
Instead of looking at C, could we just like do something similar to the problems that we're trying to solve? Does that make sense? Or both,
Sure.
even, I don't know.
Yep,
You know, something that has like
The same
unequal
force.
lengths,
yep.
The force going down.
that's going down instead of going
Sure.
one side.
So,
Yeah, this one's gonna be the one that's hard. But these, God. Goodness, I'm kind of pretty good. I think. See how my grade.
okay. So those look like all those ticks are about an equal distance apart, right?
Here.
So we got
Just an example.
a reaction here. We've got a reaction here. So, not a terribly good job of making them all same dimension, okay? Try this again, and then maybe we'll get a better right angle down here. close-ish though, right?
Yeah.
Everybody willing to suspend belief and agree that that's a right angle with my 4 freehand drawing?
I'm good.
Will that always be a right
Not necessarily. It is in these problems just because it makes the calculations easier.
So in our book, it will be.
Yep, in your book, I would say so.
On C, it's not.
Cause like
B
B
is
is not,
not.
B looks like a.
Yeah, B
B
looks
is
like a
definitely
obtuse
not.
angle.
Yeah, you're right. Yeah, B, you have an obtuse angle.
C.
C, you don't have a right angle where they're concurrent in that corner, but you do have a right angle at A, so you'll be able to make a right angle in your drawing.
Right.
Okay? And then in D, you have a right angle up at the top point.
Where the
Got it.
300 on B though cuts through, it does create a right triangle there, and then it goes into a 340. So you know, 60.
So then we'll say that from here to here, since we have 5 units, we'll just call that 5 feet. Okay? And we'll say that from here to here is 5 feet.
Help me draw it.
Then we'll say from here to here is 10 feet. Okay? Good? Okay, so what should we do for our forced polygon? Well, I guess, is there any way that we can determine any angles
You got a right on top.
that we have? We have a right angle here. Okay?
And it's 5 feet and 5 feet.
So it'll be 45 and 45.
45.
So we know that this is a 45 because we have an equilateral triangle. Doesn't make any sense because I only have a 5-foot and a 10-foot equilateral triangle. Needs to be a 30 degree.
So it can't be equilateral.
It needs to be, the 5 feet
It's
down
a-
can't be,
it's
it
a
can't be
right
5 feet
triangle.
down, it
Yeah.
needs to be, 8 feet or something, it needs to be 3, 4, 5 or something like that.
Just make that up.
Let's do it. Like a 30, 60 or something.
So we'll call that 4 feet. Now what does that tell us about this angle?
That one would be the 30, wouldn't it?
No.
No,
Nope.
Would that be the 60?
Nope.
no, it won't be a 60. So John, what would we use here to determine this angle?
Let's see, that's there, so you could use tangent,
We could use tangent, right?
should be what, 5 feet over 4.
Uh,
Or you need to use the inverse of tangent,
yep. But if we're calling this angle theta,
yeah,
right? What's our setup for tangent when we're solving it?
4 or 5, no, 5 over 4.
What do we remember? We have SOHCAHTOA, right?
X over 5 or something like
So we'd have
Oh,
opposite.
I'm sorry, I meant cosine.
Oh, cosine?
Yeah.
Well, but we don't know what this distance is.
Oh, right.
We know that this is 4 foot, and we know that this is 5 foot, so we have to use tangent. So you're right in tangent.
Can we
You just
just
have to flip.
use Pythagorean theorem to figure that out and then do?
You could use Pythagorean theorem to determine that distance. But remember, your distance doesn't have anything to do with the
Just to get-
magnitude in your force.
I know that,
So it's 4
but just to get to
five.
another formula. So if you know that distance, then you can use cosine.
that.
You could, but here we can just use tangent,
Yeah,
right?
yeah.
But yeah, if you're more familiar and you want to use cosine, yeah, then you would need to determine what your hypotenuse is. Okay?
Mhm.
Okay?
38.66.
38.6. Okay, so we'll just say that our,
I can do this.
So how do you do that?
so we'll just say that our theta is 40 degrees. Does that work for everybody in calculations? Okay? So if this is 40 degrees, what do we have here?
Wait, we're just rounding it up to 40.
Yeah, I mean, if you wanna use 39 degrees, we can use
And then
39
that would be
degrees.
50.
Guess what we do then.
Okay? And if this is a right angle, then we have the same thing over here, right?
No. So it's
Laws of
4 divided
complementary
by
angles.
5.
4 divided by
Okay,
five.
that's 1.8. So you use
Okay. Okay?
tangent inverse, 0.8. That's 30.
Everybody along for the ride so far?
Yes.
So I was just at the 38.6, and you use that, that gave us,
That's telling us this angle here, right?
okay,
Because tangent tells us, if we use the inverse of tangent
Oh, okay.
with the opposite length
You're saying you make it 40.
divided by the adjacent length, it's 38.66, right?
40 is easier, yeah.
40 is just gonna make it a little bit easier for
Okay.
our math than punching in 38.66 every
so
time
by
we
default,
calculate.
it's gotta be 50, okay.
Yep. And since we have a right angle up here, we know that this angle needs to be 90 minus our theta. Okay? Everybody's with?
So the bottom then isn't a right angle then, since that's.
No, we changed it.
What's that?
You still have the right angle symbol on that bottom.
So it's not a right angle. It's not a right angle. Otherwise the other side would be 40.
It still is.
It still is. if you're
40
looking at it
still
as a
is?
whole.
Okay, it's 50, 40.
40 degrees and
40,
50
yeah.
degrees
Okay.
together.
Yeah.
I thought those were 250s.
Oh, no.
Oh, I see, it's 40 going, no, I see it. It's a degree.
Okay. Is there anything else we need before we go to the force polygon? Or do we have everything to move on?
We're pretty good.
Okay? Does everybody agree with John? Justin? Do you agree?
Following them.
Good. Take that reference out. So, how would you like to construct? What should we draw as our first leg of our polygon?
The 500, right? Yeah.
You want to draw the vertical 500 pound first force? Okay? It's not very vertical.
It's not a right angle. The angle on the left is 60 degrees.
Oh, okay.
Oh, you're already done.
Like in that, you actually do the math on the other side.
He's rounding up. No. That was not really 40, 50.
Yeah, but the left side is actually 68. If you actually do it.
Okay? What do you want to draw next?
The,
But you wanna draw that right triangle basically, that line?
What we're investing, the angle that we, or the magnitude that we want to know?
Yes.
Okay? And what angle should I draw it at?
just parallel.
50 degrees, like Terry
Parallel to this guy, right?
Yeah.
We want to make sure that we don't change our line of action. So what is this angle then?
130. Wait.
Careful,
The
40
outer angle?
degrees.
it's 40 degrees, right?
40.
Because we want this to be
said. 90.
our 50 degrees that we've drawn in here.
Oh, I'm talking about the total.
Yep. So here we have 40 degrees from the horizontal.
50.
Needs to start looking outside.
Oh, yeah, yeah.
Okay?
So that should be at 40 degrees coming down? Or no, it would be
Interior angle would be 40.
into, yeah.
This angle.
Yeah.
Yep. Okay. So now, we can get back to, again, however we want to solve it, whether we want to solve it like how John solves it, using sine of the angle. But if we're interested in this magnitude here, which angle would we be using?
The 40 degree angle.
The 40 degree angle, okay?
I don't agree with it.
So John, if we're gonna say sine of 40 degrees, how would we set that up? What would be in our numerator?
Opposite over 100, so that'd be x over
X
500.
over 500. Okay? And so x equals 500 times sine of 40 degrees. Okay? Sine of 40 is
Seven,
about 0.65 or something?
6.4,
0.64, I mean,
whatever,
roughly.
yeah.
So
321, doing 300.
321? So 321 pounds. Okay? If we don't want to solve it this way, if we wanted to do the law of sines, how would we set it up?
First
Sorry.
designate A, B,
So
C.
sine 90 over 500.
Sine of 90
Is equal to
500 pounds.
Equal to sine 40 over x, b, whatever, c, whatever we're.
Sine of 40 over x.
Yeah.
Okay?
The numbers just don't work out.
So
So x would equal 500 pounds times sine of 40 over sine of 90. Always remember that sine of 90, that's what works out in, that's why it works out to have right angles in these. Sine of 90 always equals 1. Okay? Sine of 90 is 1, cosine of 0 is 1.
Unit circle?
What's that?
Is that the unit circle?
It's, yeah, it's from the unit circle.
Screw that.
Yep. Yep. Yeah, you don't have to, yeah. You don't have to memorize the unit circle. It just,
Okay.
anytime in these problems, you'll see it a lot in the problems, is that you'll get sine of 90 a lot.
And
Okay?
it's not even that.
Does that help with the force polygon problems?
Yeah, what exactly are you trying to find in that then?
Period.
So,
Say you get your final answer,
yep,
so like for A on 17, you got 141.42.
yep. Pounds, right? Because your degree, your angles will always be in degrees,
Okay.
right? And the sine of an angle is a unitless measurement.
there's,
Okay? The sine of an angle, or the cosine or a tangent of an angle, it's a unitless measure, okay? So we don't have units here, we don't have units here, we only have pounds, okay? So your units of force are always pounds. That's a good question, Justin. And then the other thing you have to keep in mind
is there like
is,
an angle or a,
what is the sense of these? Okay?
so by, that's where, so we got 141, 141, okay. Mine was, I put, since, if it starts down here and it's 45, would it be negative 45 degree would be your sense? Or am I completely off on? Cause it's,
No, so keep in mind what it asks you for on page 16. If you go and look at the bottom of page 16. 16 says, find the sense as tension or compression. Okay? Keep in mind that those angles, when you're talking about angles, that's telling you your line of action,
okay,
right? Sense is telling you, is my force running in this direction? Or is my force running in this direction? Okay?
okay.
Let's think about what that means for our force.
That would be.
What is happening to these cables if I grab on and pull straight down with 500 pounds of force?
Tension.
Are we, yeah, so we're
Okay,
gonna have,
so it's asking for a word, it's asking
Yep.
for tension or compression.
yep, it's tension or compression, is all you need.
So both these two are gonna be tension.
Yeah,
Yep. Yep,
okay, I.
yeah, Jay.
So, going back to the problem, how do you know to use sine?
How we know to use sine is,
Going back to the basics.
What you're given
Well, it's not necessarily what we're given, it just depends on which portion of the triangle you want to use, okay? And, well, and I guess, no, John, you do have a good point. It is dependent on what we're given. We don't know anything about this method, okay? So we don't have to use the 40-degree angle. We could use the 50-degree angle, but then we would have to use cosine, okay? So the things that I would remember are just that. Sine of some angle you don't have to do C.
But you don't have to.
We can look at C if you would like and solve it. So if you want to look at the sine of an angle, and here's your triangle. Okay? If here is theta, okay? Here is opposite, here is adjacent, here is hypotenuse. Okay? So sine is your opposite over your hypotenuse, cosine is your adjacent over your hypotenuse, tangent is your opposite over your adjacent. Okay? Do you want to look at C?
Sure.
Or should we stick with homework and go to
Go to the next.
the bridge stuff?
Yeah. Do you want to do, we can look at that, and then, yeah, if we have time left, then we can look at C, or Kurt, if you want to talk about problem C offline, I'm more than happy to.
Sure.
Okay. Does anybody need any of this information on the board any longer? We're good with it. One more second? Sure.
You're gonna post this, right?
Yeah, this will go up on the YouTube channel too, so, but if you want, if you need a little bit more time to write it down.
Make
certainly.
you go
I'm,
viral then.
Go ahead.
I want to A on your first.
Don't make those videos go viral.
I'm gonna start pumping it on my page.
Yeah.
I was your first subscriber, so.
No, I said
Oh,
I
yeah.
was, man.
You can watch the awful concrete blasting test videos that I made
Oh,
3 or 4 years ago too, that are up on there.
beautiful.
Work hard, Ben. Work hard.
They need to, yeah, well, they need to be remade, so. Okay, everybody good? Then we'll move on to looking at a bridge and analyzing moments.
Page 28.
Okay. Remind me, you just had to do 2 of these also, didn't
No,
you?
this is A through F.
How'd you do A through D? Okay.
Oh, A through D?
Yep.
Oh, I'm done. Almost makes credit. Well, never mind, because I was going to ask you a question on F.
So let's look at,
Steve, you were doing that too.
well, let's look at F.
Yeah.
I don't know that I did them right. I just did
Oh, no, because F is different than all the rest of them.
Is not-
Because the way R2 is, there's weight,
What do you mean?
well, there's weight extending after R2. None of the, oh, yeah, there is one like that. Oh, wait,
do
that's
one
E,
that
so
way,
it don't matter.
Yes.
So through A through D, there's none with R2, you see how R2.
Sure, no cantilevered elements? Okay,
Exactly.
So
So I
you
don't
don't
think
want to
that'll
look at
help
one with the
anybody.
cantilevered elements. Okay, so let's look at, how are we doing on time? Let's see. So we have 10:30, okay. So let's look at first, we'll take a span. We'll put our reactions at the termination of the spans. Let's put in 2 loads, okay? Let's put 400 pounds, and let's put 600 pounds. Okay?
So yeah, because that equals 200 anyway.
And we'll say that this is 4 feet, or that looks like it's about 6 feet, and that looks like it's about 4 feet. Okay?
So it's 10, 14, so R times 14.
So what's the total span of our bridge?
14.
14 foot. Okay? So what three conditions do we have to satisfy to have equilibrium in our bridge?
0.
R1, R2,
Also 0.
Careful, we want to know what are the values of R1 and R2, right?
yeah.
That's what we're determining.
Oh, okay, so the x plane has to be 0, the y
Yep.
plane has to be 0.
The sum of all our forces in the x direction have to equal 0, right? The sum of all our forces in the y direction have to equal 0. And what's the third case? Not magnitude. What was the other M word that we learned about in terminology? What did you say? Moment? Yep. The sum of all our moments. Okay, so what we're saying is we need to secure this bridge in such a way that it's not sliding along the plane of the bridge, or the board, right? It's not moving up and down with respect to the board, and we're not rotating, okay? Are we in agreement that all three of those cases would be bad for our bridge?
Yes.
Okay? More so, it would be bad for the people trying to use it, okay? Do we have any forces in the x direction?
No.
We don't, right? So we meet this condition. What about forces in the y direction?
Yes.
We have 1,000 pounds in the downward direction, okay? Do we want to call, when we deal with these, do we want to call forces in this direction positive or negative?
Negative.
We want to call them negative, okay? So we have minus 1,000 pounds, and then we have plus R1 and plus R2. Are we missing any forces?
No.
We've got everything, right? We've got our reactions, and we've got everything being applied to the bridge. Now, in a real-world scenario, we would have to take into account the weight of the bridge itself, right? But we're assuming we're working in 2 dimensions, this thing is uniformly thin, it's infinitesimally small, okay? And so we don't have to take that into account. So, we don't have to worry about that, but in the real world, this is something that designers have to take into account, okay? What about our moments? Do we know anything about that at this point? We don't, right? So, we can't solve this at this point, right? Because we have an equation with 2 variables, but only 1 solution, okay? So what would be the first step that we could take in trying to solve this?
So 1,000
Yep.
equals to R1 plus R2.
Okay? Okay, I agree with you there. Is there any way that we can isolate R1 or R2 from an equation? Does anyone remember? What's the formula for calculating a moment?
Distance times force.
Force times distance, right?
Negative force times moment.
So if we have a distance of 0, what will our moment be? Regardless of the magnitude of the force. It'll be 0, right? Oops. Okay? So is there any way that we can look at a moment to isolate either the reaction at points 1 or points 2? Could we look at the moment around the reaction at point 1?
Yeah.
Okay?
Well, what the book says is you take 4,000 times the distance from R2,
And then the
and then
6,000.
the 6,000 times the distance from R2, add them together and subtract them from R1.
Well, you
Times the
divide it by,
distance
no, so
Okay, so you wanna look about 0.2.
Correct.
Either is fine. Okay, so let's look at moments around R2. Okay? And let's also keep in mind, how do we determine if we have a positive moment? Do you remember?
Clockwise.
Yeah, so when we go to grab on to the element with our thumb pointing out of the plane, if it's curling clockwise, it's a positive element, okay? So R1 will have a positive value, okay? And we multiply it by the entire distance of the bridge because that's how far away it is from the reaction, okay? Does everyone follow that? With me so far? Okay? How about this guy? Our 400-pound force.
400 times 10.
What's the magnitude of 400? What happens if we grab onto the bridge like this? Are we going to rotate like this? Or are we going to rotate like this?
From R2, it's gonna be negative.
From R2, it's going to be negative. Okay?
So the way the book has it, you'd be minusing a negative, so that's why I just called it.
Yeah, that's a good point, thank you, yes. And your book automatically distributes your negative, okay? Which is fine by multiplication.
So there wouldn't be.
This
no
is
plus
the
sign,
same.
it'd be R1 times 14 minus the 400 times 2.
So is 400 negative because it's smaller than 600? Is that why?
No, because it's
No,
a negative
what side
force. We already determined that. The force is going down,
Down.
negative,
Careful,
right? Or
careful.
It's not.
It doesn't have anything to do with the magnitude of the force. It has to do with what type of rotation
from the moment, yeah.
it's making around
Is it-
the point in question.
So it has to do with where.
It has to be where we're referencing, okay? If we're looking at R2, okay, and we apply a 400-pound force 10 feet away, that force wants to rotate in this direction. Wants to rotate counterclockwise.
Wouldn't both of those be negative unless the R2 is in the
Yep.
middle? Okay.
They'll both be negative on, Marshall makes a very good point, they'll both be negative on R2. How will they react at R1 though?
Positive.
They'll react in a positive way, right? Okay? And that makes sense with, I mean, when we think about a bridge deck, what's happening with the bridge deck when we apply a load at the middle, right? It's trying to deform the bridge this way, okay? It's trying to pull in a counterclockwise method this reaction, and it's trying to pull on this reaction in a counterclockwise method, okay? So that's where the negatives and positives come from, okay? But yeah, Marshall brings up a good point. This one will also be negative, okay?
So it'd be minus 600 times.
Yep, so it would be minus 600 times, we're 4 feet away. Or if you're following the book's notation where they're just automatically distributing that. Oops, I should have wrote pounds in there, sorry. What?
No, I was talking about.
Okay. Does everybody agree, though, that these are equivalent statements? Do we have any issue between these statements? Good? Marshall, do you have an issue?
No, I was just figuring. I got it.
Okay.
Yeah.
Okay. Then from here, we're just plugging and chugging, right? So. Okay. And so, in order for this reaction to stay in its place, what does this equation have to equal?
Yeah.
It has to equal 0, right? So then, could we also say that 14 R1 pound-feet equals 6,400 pound-feet.
And then you get the R1 by yourself, you divide it by 14.
And then just divide both sides by 14.
So 200.
So R1's what,
200.
400, huh?
Is it
450?
64 by 14?
Something like that?
457.1.
457?
Yeah.
Okay?
So R2 would just be the total. 6,400 minus.
Oh, I'm sorry. We changed and we're looking at R2. I apologize. I wrote down R2 and then started switch back to R1.
So then, because now you make it 0, you just do 1,000 minus 457.1 to get R1.
Yep, exactly right. Yep. So does everybody follow what Terry said? Remember that we started, our forces in the y direction, we had 2 unknowns. We use this condition to determine R2. And so what Terry's saying is, I know this 1,000 pounds, I don't know R1, but I know R2. If I take 1,000 pounds equals R1 plus 457.1 pounds, R1 will equal 1,000 pounds
Finally, some math that makes sense.
minus 457.1 pounds.
So it's like 540.
So 542.9.
So just to clarify something.
Yep.
Same equation, same pathway going across. The book calls it R1.
Referring to that.
So you take the total length and then you work out each one of these same way. And you're figuring for R1. And then to get R2, you take the sum of this minus the total and that'll give you R2. So see how you get this.
R1.
And R2 would be the total, the 8,000.
No, this is looking at it from the right-hand side.
But it's calling it R1.
Correct. Because we have to keep in mind that if we're looking at R2, right?
Mhm.
What's the reaction force in R2? I mean, we know that now. But back here when we didn't know either of those reactions. The moment about R2, for the reaction at R2, is R2 times 0 feet, right? So that doesn't come into play. What it's telling you is that this distance,
The 14 feet?
yep, 14 feet times R1.
So it'd be 14 feet times 457.
Yep. Okay.
Or no, it'd be, that's not, it'd be 552.
I know, but in the book it says the exact opposite.
Wait, so
I mean,
that's,
my R1
so what does that
is
find
completely
when you
backwards.
times that, what is that finding?
I get what you mean, Rush.
See what I'm
This is
saying?
opposite.
Yeah, it's
What's
exactly
going
the
on
opposite
in
of
the
what's in the book.
Oh!
You get what I'm saying? man?
Yeah,
It's R1, thank you.
yes. This is R1. I was right initially, sorry.
I'm so confused.
It's the same
It's
thing.
because it's
You
just,
start with R1,
Yep.
and you go
you're
across.
looking at the magnitude of R2, so you're gonna be going.
Yep,
So you figure for R1.
You're
Yep.
measuring your.
we're measuring about R2, okay?
But you start with
R1 is
R1,
14 feet.
14 feet.
Yep,
You solve that
Yep.
and that'll give you your R2. It's the same thing, it's just, it was just confusing me a little
Same
bit.
thing, but different.
Yeah, same thing.
sorry, I had the nomenclature correct and changed it in the middle. That's what caused you the
Okay.
confusion, okay? Do we want to look at one where we have a uniformly distributed load? Over the length, okay? Do we need more time with this? writing down some things.
So how would you tell if that checks out? Is it? So you just see if
R1
R1 and
R2 would
R2
equal
equal.
1,000, the total number of force, so the 400,
Yep.
600,000, R1 plus R2 should equal. And that would make
And
it
then
zero.
how would you do?
Are you asking about the moments, Justin?
Right.
So here we solved for the moment about R2. We could also solve for the moment about R1 if you would like.
And if they add up to 1,000.
Okay, yeah,
The difference.
It's not saying that you have to solve for moments at every point
right, I get,
on the bridge. It's
I
just
get that.
saying anytime you're looking at a moment, it has to
the
equal
moment
zero.
of R2 would equal what? R1?
Nope, remember that we want this bridge to stay in place, right?
Yep.
So we need to make sure if our moment about R2 does not equal 0, what does it mean for this reaction?
It's going negative.
We're going to yank that reaction point out of its pier or out of the ground or whatever it's tied into, okay? If the moment is non-zero, we don't have static equilibrium and we're moving.
You found the R1 and then you're gonna take that back up and plug it into your equation.
Yep. What does this mean for us in industry? What does it mean for us when we're actually constructing these things? I don't care if reaction 1 has 500 pounds resistance. I don't care if it has 1,000 pounds resistance. I don't care if it has 2,000 pounds resistance. Okay? What we're doing then is we're just making a more stout element. Okay? But if our reaction at 1 can only support 400 pounds in the vertical direction, it's going to get ripped right out of that location. Okay? It's not going to be pulled straight up. It's going to be rotated out of place. Okay? Does that help visualize what it is that we're after with this? So we're going to look at a couple other things. We're going to look at axial forces. We're going to look at shear as well. So it's just one of the types of ways that these elements can fail. Okay? I don't know. Does that give you a better understanding of what we're after,
I
Justin?
understand that. It's just
You have to go backwards the other way.
because we're only doing part of it, so I'm confused on exactly what we're trying to.
So the
Like I
check
get what we're
working
trying
if
to
you went the other way,
find, but
from R1.
so you have to do that whole thing over again for.
For R1?
So R1 will be a different.
In this problem, we don't, because we only have the two unknowns. Okay? Once we got done here, we can go to our force in the vertical direction, because here we know that R1 plus R2 equals 1,000 pounds.
Right.
Here we were able to determine R1,
Right.
so now it's
Which
just
gives you-
simple solving.
Your force of your
Yep.
Y, but what about your moments?
We can solve that as well. Okay, so what would we want to set it up to be? Then we're just working we're working from the other side.
That's what I'm asking. Is you have to do that again.
No.
Because it'll
You
give you
have
the
to check your-
452.9 or 542.9.
Those are the moments, those are the
So-
numbers for it.
Two answers to your question. For this class, and this is the first answer that I'll give you because this is what you're going to care about, right? For the purpose of this problem, you don't have to do both of these.
Okay.
Okay? In the real world, when we're dealing with a real bridge, right? We're going to have an element here with a support. We're going to have an element here with another support. So every time that you have one of those elements, yes, those have to be checked. But no, for the conditions of these problems, you don't have to check the moments at each of these equations. Because what this tells you is this tells you the load at R1 that doesn't allow for any rotation. Okay?
So 1,000 minus that, 542.1.
Once we stop the rotation
So it's just a difference.
in the one direction, if we only have two simply supported